All right, this dance pop music. This is episode 205, atmospheric electricity. Let's start out by reading something from this book that I have called Thunder and Lightning. So, Steve Marshbourne, with his wife Joyce, is the founder of Lightning Strike and Electric Shock Survivors International Incorporated. So, Steve Marshbourne says, in 1969, I was struck by lightning. I was 25. It was a beautiful day. I was sitting on a teller stool inside the bank where I was employed. One bolt of lightning strayed from a storm 12 miles away and hit our drive-through window speaker. Back in 69, there was no direct deposit. The bank cashed your check. So we had 2 to 3 long lines flowing outside the bank. Everybody that was inside the bank saw it happen. The lightning went straight into my back. My feet were on the metal rungs of the stool. Lightning exited one leg. I had a metal teller stamp in the other hand. I was stamping a deposit, and the lightning exited that hand. I thought I would never get home to my wife. I thought I would never see my child that was to be born the next month. I could hear, but I couldn't speak. I felt like the left side of my brain had blown out. I knew now it had been scorched. My head was in intense pain. My back, it felt like I'd been split with a machete. A person hit by lightning may not show any visible sign of injury. In other cases, a person's skin may appear tattooed with a network of spidery branches called Lichtenberg figures, also known as lightning flowers, filigree bruises that mark the path of electrical energy. In developed countries, 90% of people struck by lightning survive. The other 10% are likely to die, not from burns as is often assumed, but from cardiac arrest. So, skipping over some other parts, Steve Marshall says, actually, you know what? Let me see. In the volume of stories published by Marshmore's Lightning Strikes and Electric Shock Survivors International, survivors described the moment they were hit. Carol Dawson, former assistant coach of the Houston Rockets, was playing golf in 1990 when his club caught a streamer. I felt lit up like a Christmas tree. Dawson lost his eyesight. Stephen Melvin remembers a loud sizzle like a steak on a grill, then a bright flash. W.J. Sichansky saw nothing, heard nothing, felt nothing when he and a fellow non-commissioned officer were struck by lightning in 1945 in Mineral Wells, Texas, a town I've been to, by the way. But a witness reported seeing a halo of fire around their heads and their clothes bursting into flames. Sichansky spent 4 months in the hospital and is unsure which of his subsequent ailments, hearing loss, arthritis, insomnia, might be due to the strike. The other officer was killed. Electricity and heat shock find idiosyncratic pathways through each body. The brain, heart, and other organs are all vulnerable. Victims may experience seizures, deafness, blindness, chest pains, nausea, headaches, confusion, and amnesia. Some patients have described dramatic weight loss, tingling hands, muscle twitches, loss of temperature sensation, extreme thirst, temporary paralysis, and moments of clinical death. Usually, it takes a while for certain problems to manifest. All right, so I could go on, but this book isn't.
Wait. What?
It's a pretty beautiful book, by the way, called Thunder and Lightning: Weather Past, Present, and Future by Lauren Redness.
Yeah. What is this? What are we watching?
But before I continue, and I finished concluding reading that little page, what? Oh, and it dropped on the floor. Wow. Okay, that was dramatic. What are we doing here, right? The disembodied voice in the background always asks this question. Well, guess what? This is SG2 on Space, the only weekly space show. So we are streaming this live on this. If you're watching this live, this is Friday, March 22nd, 2024, by the Gregorian calendar.
And on the planet Earth.
On the planet Earth, the local time here in Houston, Texas, United States of America, is 5:40 something p.m., 5:49 p.m. So today's episode is episode 205. We've been doing this a while, and we're going to do it we're going to talk about atmospheric electricity. We have, I think, done this episode once. I mean, some similar topic to this before. Before I continue, thank you to Patreon supporters, patreon.com/SG2 on Space. Thank you for Kyle Baker, Sam Welsh, and John Graves for your kindly monthly donations. Without you, I would still do the show. But thank you anyway, since there's always motivation to know there are supporters and viewers, that's for sure. Now, who is that disembodied voice? It is none other than the headband guy.
Hey, Shen.
Leonard Kramer. That's
Shen. And I'm pointing in the right direction.
Yes, you are. It's embarrassing when you don't point in the right direction.
Yeah, but I'm well trained now. I've rewired my nervous system, so I know that right is left and left
Well
is
trained
right.
indeed. All right. I'm gonna leave the ticker running in the bottom just so that everyone knows who.
Yep.
Thank you to the patrons. With all that said, let's just jump right in the show here. So atmospheric electricity. We all know about lightning, or we think we do, but there's more to it than that, right? What exactly is atmospheric electricity?
Oh, well, I guess I just thought we'd have a conversation about that because it's pretty interesting.
Okay, I
Um,
guess we,
it,
we
the
can.
the so lightning is just the one aspect of it. And in fact, there's something very interesting about the Earth's atmosphere, and that is that there's something called the clear air electric field, and it's global. In other words, it's something that occurs all over the Earth.
Did
Any
you just say
place
the clear air electric field?
clear air electric field.
Huh.
So although thunderstorms, you obviously see that there's some electrical activity going on there. It turns out that all over the Earth, wherever the air is clear, in fair weather, there's an opposite current that's flowing, and it's flowing downward. The thunderstorms produce a net current upward. In other words, the electrons come down. The electrons are negative particles, and they go opposite in the direction of the. Oh, that's Richard Feynman.
Yeah, I figure you might appreciate Richard Feynman.
Yeah. Okay. Yeah. So this is very important. Actually, this is a very good article about it. I think this is one of his lectures.
Yeah, this is from the Feynman lectures in
from 1962, and the reason so it's actually pretty interesting. One of the things that's interesting about it is that very little progress has been made in 100 years in understanding the source of lightning and atmospheric electricity. Now, I think that the clear air current that occurs, I think, is pretty interesting. What happens is that, okay, the phenomenon. Let's just talk about what happens in fair weather, and that's there's a situation everywhere on Earth. There's an electric field, and it's about 100 volts per meter, something like that. So at the top of your head, the top of your head is 100 volts higher in potential than where your feet are. And so you're wondering, well, if that's true, well, then why don't I just use a wire to conduct electricity? Well, it's because the atmosphere has so little conductivity that actually you're a much better conductor, and so you end up filling up with the electrons from the Earth. So the Earth is negatively charged, and so you carry the charge with you. So the figure there is really good because you see the above part showing the electric field. I hope he's showing the field pointing down, right? Yeah. So the electric field is pointing down, and then when you're standing there, well, you kind of like become part of the ground because relatively speaking, you're a very, very much better conductor than the air, right? So, but we know that this exists because actually, I think even back in the 19th century, late 19th century, you can take a conductor, like some kind of like a bucket, say a metal bucket, and you can suspend it at above the ground, maybe on a dielectric, some non-conducting pole, or suspend it from silk or some kind of um, um, rope or something that doesn't conduct electricity. And if you just leave it there and then bring it down, you can measure a little spark or a little.
Like something like this.
Well, no. Okay, that's another phenomenon. So what I was talking about with the bucket, if you just hold a bucket above, at a high altitude, or a big metal sphere or something higher elevation, say 30 feet above the ground, it will assume that potential, and then when you can bring it down, and if you're quick about it, you can measure that there's a voltage. You can get it works better if you have a bucket, like a metal bucket full of water, and it has a little hole in it. And so then you raise the bucket full of water up high at higher elevation and let the water drip out, and that'll carry the charge away faster, and then it works faster that way. But either way, that other phenomena that you were talking about, that's another way. What you can do is you can and I have to say, I've always wanted to do this, but I confess I've never actually done this, but I think it's a straightforward thing to do. You take a metal sheet, like a piece of aluminum sheet, and you isolate it from the ground so that it's not in direct contact with the ground, except at a particular grounding spot. In other words, you make sure that it's well grounded at one point, right? And then you allow it to come to the same potential as the Earth. Then you disconnect it from the ground and you cover it with another sheet so that it's kind of like inside of a box, as it were. Then you can measure a potential difference between the cover, the metal that you've covered it, and the isolated conductor in the middle. And this is consistent throughout the world. People have measured this everywhere. And associated with this electric field, which points down everywhere, is a very small, what they call fair weather or clear air electric current. And of course, I just said that the atmosphere is not a very good conductor, but it's not a
Well, I think
perfect insulator.
I mean, is this what you're talking about?
Oh yeah, well, I forgot what that's called, but we'll get to that in a second. That's very interesting. That's one of the things that I'm really interested in, and I'll explain that in a second. So everywhere on Earth, there's this potential difference between the ground of the Earth and ultimately a layer about 50 kilometers above it. This is not in the ionosphere. Okay, it's still well below the ionosphere, but
you said 50 kilometers, right?
50 kilometers, about 40 or 50 kilometers.
I think this is what you're talking about. This thing.
Oh,
right?
Yeah,
yeah.
And the voltage up there is something on the order of 400,000 volts, right? So if you take the 400,000 volts and you divide it by that distance, it's roughly 100 volts per meter, and so and that's everywhere on Earth, and it does vary. It does vary, from time to time. The voltage can vary locally from place to place. The current is pretty much constant. I think it's like 10 to the minus something like 10 to the minus 12. What?
Well, it says 10 to the minus 12 it's right there.
Okay, so that's a micro amp. Okay, which is pretty small, but there's a lot. That's per square meter, but there's a lot of square meters. Right.
Well, the total electric current reaching the Earth's surface at any time is very nearly constant, 1800 amperes.
Okay.
This current, of course, is positive. It carries positive charge. It carries plus charges to Earth. So we have voltage.
It's carrying a current to the Earth, and this is all connected to the thunderstorm activity. Okay, which we'll get to in a second. So that other graph that you had there, I forgot what that's called. But it turns out
potential gradient.
The variation of the current wherever you are on Earth varies as in the Earth fixed frame. Meaning, let me see how I can say this. At Greenwich, the Greenwich meridian, the constant time, the voltage, it varies by about 15 to 20%, and it's a maximum in the early evening at Greenwich. And it's a minimum in very early morning at Greenwich, England. So and that's independent of where you are on the Earth. So if I were to measure it in where we are in Houston, or if I were to measure it in Beijing,
right,
or Africa, or Europe, I would get this same curve. It's it's noisy, but if I average, I would get this exact same curve that's fixed relative to the local time at Greenwich. So it's like the absolute time of the Earth. And so that's a very mysterious kind of thing, and people wondered about that. This was discovered in the early 20th century, and people wondered about that. And they thought, well, um, uh, and it is actually, that is something that would be necessary for a constant potential at 50 kilometers, because that means that the voltage everywhere on Earth, is roughly the same, and then the voltage at 50 kilometers or 40 or 50 kilometers, wherever that level is all the same. And then, so why does it do this? And it turns out that the thunderstorms in Brazil and in Africa and all over the earth, there's tens of thousands of thunderstorms and maybe
Wow. It depends on
200 lightning flashes per second everywhere on the earth. 100 to 200 lightning flashes per second everywhere on Earth. That those are geographically fixed, and so in the late afternoon, in Brazil, for example, or over the Amazon, there's a lot of thunderstorm activity, and that's at the point where the current is maximum.
absolute
And
time on the Earth, not upon the
so
local time of the place of observation.
and I think, modern people in modern times, this article, I think, is quite old, but I don't think any progress has really been made understanding it any better than that. I think it has been. And so this thunderstorm. So let me see what else. There's another thing I wanted to say about it. In the early 20th century, people thought that they were trying to explain why there's a current in the air, because the air is an insulator, right? It doesn't conduct electricity, but it turns out that there are ions, right? Little, ions are like the atoms are stripped of an electron, or they get an extra electron, and so they will move a little bit, and so the original thought was that the ions in the atmosphere were being caused by radioactive elements, like the radioactive elements of the Earth, like potassium and maybe uranium and other kinds of things, because they give off beta, which are high energy electrons, and alpha particles, and they will strip the electrons from air. And so that was known, and so that was the assumption. But then somebody in the I don't remember, I don't remember who it was, but somebody there was a research effort to try to measure the ion concentration, the ion density, or the number of ions at high altitude in balloons. And they thought, well, if we go to a higher altitude, we should see a drop in the conductivity of the atmosphere, because these ions would be less, because it's further from the source of the ionization. But turned out it was wrong, that it increased. So ionization at high altitude increased up to, which was explaining why the conductivity was increasing, because when you go higher, the air also gets less dense, there's fewer collisions, and so if you have some ions, they have a much longer mean free path. And so, although it's not like a copper conductor up there, the fact the thing the important feature is that the conductivity of that layer at 50 kilometers is so much greater than anywhere else, that it's effectively a perfectly conducting. It's relatively perfectly conducting, if that means if it says that, relative to the rest of the atmosphere and the surface of the Earth. The solid body of the Earth is a very good conductor compared to all these other things. So you were going to ask something.
Did you explain? Okay.
So what I was going to say is, and when they discovered that, that was a big deal. I mean, in about 1912, 1915.
What is this discovery called?
I guess they discovered cosmic rays. It led to a whole branch. It was like a disaster.
Okay.
It was a big deal. It's like, why is the air, why is the air ionizing at higher altitude? It should be, so that was the discovery of cosmic rays and radiation in the
right
space
here.
environment.
Some physicists carried an experiment up to balloons and measuring ionization of the air, blah, blah, blah. Discover the opposite of ionization per unit increases attitude.
Yeah.
Cosmic rays.
Cosmic rays. That was the whole brand. Am I right with a date? Does he? I've forgotten. It
Yeah,
should be. It
1912.
should be around 1912. Did I 1912?
So we will
So
not. It's like Feynman's like we will not discuss the subject of cosmic rays now, except to say that they maintain the supply of ions. Although the ions are being swept away all the time, new ones are being created by the cosmic ray particles coming from the outside.
yeah. So
Huh.
it puts a limit on. It gives the atmosphere a very small amount of conductivity, and so the main thing to take away from this is that there's well, I mean the cosmic rays are a big deal, but that's not that and they do contribute to the atmospheric electric current that we're talking about. Um, and the fact that the conductivity of the atmosphere increases. In other words, conductivity means the ability of the atmosphere to conduct electricity increases with altitude up to about 50 kilometers, and
Right.
and so and I think the total amount. I don't know what the total amount of charge is, but it's like 1,800. Did you say 1,800? Did Feynman say 1,800?
Yeah, it's the thunderstorms throughout the world that are charging the Earth with an average of 1,800 amperes, which is then being discharged through
Okay.
regions of fair weather.
So it would only take, so what I understand is that it
That's
wouldn't
really
take,
interesting that the
yeah,
bolts of lightning don't discharge the potential.
they they don't
Okay.
they don't really discharge that potential. They increase that potential. They create that potential. And so if you just let the clear air current discharge that, it would discharge in, I don't know, a couple hours.
Right, but it
Something
doesn't
like
happen.
that.
Why is that again?
So because the lightning storms act as a dynamo that's constantly tens of thousands of lightning flashes all over the earth that are going on all the time act like
40,000 thunderstorms. Yeah.
they act like a dynamo or a
Batteries pumping electricity upper layer and maintaining the voltage. Oh wow! So lightning, I did not know that. I thought lightning discharged, but lightning really creates a voltage difference.
lightning.
Potential
Yeah,
difference.
the thunderstorms are the energy source that contributes to the atmospheric electric current.
That's
right.
the opposite of what a lot of people think, I guess.
Yeah, I think that is true. Although it is sort of there is a little bit of semantics to it,
Yeah.
because you could think of
But how do
you could
they
think of it as-
thunderstorms form?
well, thunderstorms form because I don't really know a lot about thunderstorms, in great detail, except that during the day when the surface of the Earth is heated, then the atmosphere, warm air will start to rise. But and people know that, but so the idea is that if you have warm, moist air, okay, so when the warm air rises, all right, let me see if I get this right. When the warm air rises, it cools off, right? And so cooling off, and then ordinarily you'll just have like an equilibrium. So if I just have air, like in a column, well, some of the warm air at the bottom will rise to a certain level until it reaches, equilibrium, because it gets cooler and less dense, and so then it'll stop, and that equilibrium contributes to a lapse rate in the temperature as you go higher in altitude. So on Earth, for dry air, it's something like 10 Kelvin per kilometer, or something of that order. So that's called adiabatic lapse rate. But if you have moist air, then it's at a different. It decreases. It doesn't decrease as quickly. So moist air is because there's an energy supply. When the moist air rises, it tends to condense, which then further heats the air, and then you can have a situation where you have instability, right? So if I have moist air, and we've all seen this with a thunderstorm, moist air will start to rise, and then it will cool off, and then the atmosphere, the moisture will condense out of it, which then actually liberates heat, which causes it to rise more. So it sort of goes super adiabatic, a super adiabatic lapse rate, or updraft, and these updrafts will then pull in more and train more air, right? And you'll see. So that's the manifestation of the thunderstorm. So when you see a thunderstorm far away, and everybody's seen this, you can even see the rain coming down, and you see it climbing to very high altitudes, and then it flattens out at the top. Well, that flattening is where it's hitting the stratosphere. The stratosphere is where the temperature profile flattens out because the atmosphere is in radiative equilibrium. It starts to become radiatively in equilibrium. So when you see a thunderstorm, that's heat transfer from the surface of the Earth
Kind of
to
like this, right?
to space. So all of that atmosphere, so all that energy is being overturned. And then there's another thing that happens is that it entrains cool dry air from the sides,
Mm-hmm.
and then those contribute to downdrafts. So you have updrafts, and they can be 60 can be very fast, 60 meters per second, something of that order. But and then downdrafts are also associated with all of this, and they have practical applications, for like everybody knows about microbursts. And one of the things about reading the literature as a physicist is that that there's a lot of stuff that people talk about when I read about lightning and thunderstorms and weather that I'm not, I'm interested in the physics. I'm interested in those other things too, but
Yeah.
there's a great concentration on, lightning protection and all these practical
Leonard, I'm sure you
things.
find all that very boring.
No, I don't find it boring. I find it quite
Oh.
essential and quite valuable to know about. It's just that I feel like there's very little progress has been made in this area, and so, but it is interesting. And then you have to ask, well, so what happens that, yeah, right. So what causes the lightning? And I think I have a little bit better than just arm waving to talk about.
Okay.
So you have to. Well, this is sort of the structure of what the lightning is, but the first thing that has to happen is there has to be some kind of charge separation.
Formation of the step leader.
Yeah. So there has to be some kind of charge separation.
Okay, I see.
And that's quite a challenge, from the physicists.
Right. A lot of, I guess it's still not completely fully understood, right?
I think that's an understatement. Yeah.
Yeah.
And one of the problems is that it's difficult. There's something going on a very large, very large scale that we can't replicate in the laboratory. I think that you
can try to make artificial lightning, but it's not the same as how nature does it.
We've flown airplanes through thunderstorms and measured the potential. You can use instrumentation to look at the entire dipole character of a thunderstorm. In other words, you can see the charge separation, and we know that the time constant when you have a lightning discharge, it takes about 5 to 10 seconds for the entire thing to charge up again. But the origin of the current of the electricity is just a very difficult thing to understand. There were theories, some theories that I think are still existing that are still prevailing. One of them is attributed to somebody named Wilson. And then there's another one. And so there's this idea that one of the observations is that if you have, and that can be done in the laboratory, is if you have liquid droplets and they're in a wind stream, that the wind stream will pull electrons away from the droplet. So if you have a droplet, I'm not exactly sure how the measurement was done, but if you maintain a droplet and measure the electrical potential of a liquid droplet in flowing air, if the wind is blowing fast enough to start breaking up the droplets, it pulls electrons away, so that it leaves the droplet positively charged. And so the idea is, so then that positively charged droplet then can move right in a thunderstorm because of the downdrafts and updrafts. And I'm not sure that that's right. And that's one theory.
That is one theory, and there are more. But
what?
We're hitting close to time.
Okay. Well, that's so. Anyway, yeah. So. Okay.
I want to talk about one of my favorite topics, aside from lightning, that we haven't went into in a while.
Of course, we haven't done that in a while.
Yeah, why not? Okay, there's this one called UFOs shoot green lasers. Obviously. And hold on one second. I gotta do my little alien thing. Let's
Oh,
look
I
at
want
plot.
one. I want one of those.
Here's a cow.
Oh no, it doesn't mutilate the cow, does it? That would be
No.
horrible.
Let's see.
I can hear the cow.
Alright, this is
Cow's
great.
crying.
Let's see, it's a little. Alright, anyways.
Where did you get that? At the Neil's bar?
No, a friend of mine gave it to me. I have no idea where you would get this. Okay, it's powering off. Did it power off? Yeah, it powered off. It powered off.
Yeah.
Alright, so with that aside, okay, so supposedly there's this UFOs that's shooting green lasers. Tell me if you notice anything. I'm gonna start playing this. I've not seen this. This is in Milton Keynes, England. So you tell me.
Looks like some of those sprites that you
looks real.
sometimes see we didn't get
Okay,
to.
let me see this.
All right, this is
Okay,
pretty
what does
silly.
that look like to you?
It looks like, well, obviously it's a
You're
UFO.
gonna
Of
shoot
course.
green lasers, right?
Yeah, don't be shooting green lasers.
Look at that. Look at that. What else could it be?
It's a green laser. Don't be shooting green lasers at airplanes. There's a whole bunch of people I think were arrested in Mexico for.
Look at that. What could that be? See? Okay, if we okay, fast forward a little bit. Look at that thing.
It's a green
could that
laser. I have a little laser around here somewhere. Where's
I mean,
my
that
laser?
thing in the sky is shooting laser beams up and down, right? Like, what could that be?
I don't know where my laser is.
I mean, if you see something like this, wouldn't you wonder?
I would think that somebody is shining a laser up into the sky. That's what I would think.
Then what is this light over here?
It's a cloud.
Okay, let me see some more. Okay, eventually I think it disappears. Yeah, okay, there's more.
Well, okay.
See? Like that thing over there. Oh, you think it's just somebody's only, like...
Yeah, I just saw something in the...
Like, yeah, this person zoomed in with a camera. And it's like, what is that flying thing, you know?
All right.
Shining. Like, it's remarkable.
I just saw something in the news. I think there was a concert or a fireworks display or something in Mexico, and a whole lot of people had these lasers, and they were shining it on an airplane, and they're in big trouble because you can blind the airplane.
Yeah, you definitely can. Although, so Tom Marvin from Broughton captured this in a video. He said, it first caught our attention as a beam shone through our bedroom window and it was bright. My first thought was that was a searchlight from a police helicopter, but after seeing the light shine as high into the sky as we could see, we knew it wasn't. The laser reportedly acted in the Kingston area of the town around 10 people.
No, it's a drone with a laser.
September 24th, 2023. Okay.
Yeah, with drones now, what are we going to do? What are we going to do about UFOs? Because now everything can be attributed to drones.
Oh my gosh. Well, right. I don't know what this is, but I don't know. It doesn't seem like the typical, this phenomenon, right? With the cows and everything. I mean, you don't have to have cows, but
apparently you do. I don't.
Okay. All right. Well, with that, I think we did a pretty good brief intro on what the atmospheric electricity, how that's formed, what thunderstorms are, what lightning is.
Good enough.
Good enough for now. So, as all of you know, we do the show every week. We will be back next week.
We say that we do it every week.
Okay, we say it. We say we do. All right, fine. We say we do.
We have schedules and busy lives and so forth.
It happens. Mm-hmm. But with all that said, support the show on patreon.com/SG2 on space. Thank you again for Kyle Baker, Sam Welsh, and John Grace for your donations. And
what about Atum Ra?
And Atum Ra, of course, for essentially helping to making sure this show was a success before I started actually doing the producer part.
Being a good guy.
Exactly. You can find this show on YouTube. and so you can go on youtube.com/ashingo/streams. You can
can
also look up
like and subscribe and
like,
send
subscribe, and
it to your
share.
friends. Tell all your friends.
Exactly. And for our viewers that are 10,000 years in the future,
Yeah,
well,
I always want to say something.
I'm sure you already figured out what lightning and thunderstorms are.
I'm not sure. I'm not.
Maybe not. Okay, so for cultural reasons, I don't know. Yes, so the headband is not atypical of the attire for people in the 21st century.
And neither is my shirt, but
You know,
it's me.
But you know, the kitchen back there is pretty ordinary. You know, hey, paper books still exist, as I was saying. So you know, that's
I just ordered a Kindle, like a Kindle.
Yeah.
One that you can write. I think it's called a Kindle Scribe or something. So I've moved into
that's wonderful.
I have moved into the Kindle world.
Okay.
It's fine.
People in the future realize that we still use paper, although some of us are transitioning to the digital world.
Mm-hmm.
So, with all that said,
and we are rebelling against the plastic. We're sorry about that, by the way. I'm sure it's everywhere. Yeah.
Okay. All right, everyone. I will say, what is the thing I say? Namaste, and then you do the
shalom and
yeah. Yes, there you go.
Good night.
Good night, everyone.
Oh my God. Good night, everyone.
So fun.